Okay, hello and welcome to today's Digital Lunch and Learn with Dr. Bill Capehart. Just some housekeeping things before we get started. This event is recorded and I will upload it to our YouTube channel afterwards. And everyone can, if in the chat function, just switch it to all panelists, but everyone's always curious who's here. So if everyone can just put their name, their class and their major, everyone likes to see that. So without further ado, please welcome Dr. Bill Capehart.
All right. All right, am I on? Yes, I am. Hi, I am Bill Capehart. I am a faculty member in the Civil Environmental Engineering Department, and I also run the Atmospheric and Environmental Science program here at South Dakota School of Mines. And my specialty has typically been, through my career, working with the interface between water, weather, and climate. In fact, the civils knew more about what I was doing than the meteorology people very often when I was getting my degree. And my work area has changed in recent years with respect to working in areas such as climate change and also the interaction between climate change and our built environment. So if you'll excuse me, I'm actually trying to set my environment up here. All right. Sarah, if you can come in and make sure that I'm actually showing my slides.
Yep, you're good. I can see them.
All right. Okay. So what I'm going to talk about today is really the intersection of climate change and our infrastructure. And a lot of it is going to be more toward Great Plains infrastructure. I will be talking about some other sectors that will be rather sketchy points that do keep me up at night occasionally. I also have a more pithy term when people ask what I do. Very often I just talk about, say, I talk about how climate change breaks your stuff. All right, and it is something that is increasingly something that we are very worried about. One of the things I'm also going to do here is I'm going to credit some of the people who I've worked with on these projects. A big group is a group out of the National Center for Atmospheric Research, specifically a group from the Capacity Center for Weather and Extremes. They're the one that got me into this trouble. And there's another subgroup. It's called the Engineering for Climate Extremes Partnership. And their job has been to really focus an area of research on the interface between how climate change really impacts our built environment. And from that started a thing with the American Society of Civil Engineers and a committee, specifically the Committee for Adaptation for a Changing Climate, call it the CAC, so we don't have to worry about acronyms. And in meteorology, as I think Ken may notice, I see he's on there, we speak in acronyms mostly, so I'm going to try to behave today. But also we have, we're at a task force which was really to investigate how the future weather and climate extremes that we expect to have are going to impact on things like the infrastructure report card, which I'm going to get to shortly in this presentation. But if we look at one of the things that does have us very much concerned is really our fragility as a country and also as a world with interactive systems. The situation we have here is, for example, in 2021, we had a large number of over 10, usually that's how we tend to count it. Okay, how many consecutive years have we had with events that are 1 billion in excess in total costs? And those are specifically weather and climate oriented events. And typically those are going to be things like droughts, things that can be associated and attributed to weather. So you're not seeing things like volcanic eruptions. You're not seeing things like changes in not seeing things like geopolitical issues, or also, being hit with meteors and stuff like that. We don't have to worry about that yet, but we do talk sometimes about earthquakes and things like that when we talk about disasters to infrastructure. But in the United States, okay, this was our 7th year where we've had at least 10 incidences with a price tag of 1 billion at least. And here's actually another plot. This is the both the number of events, those are the bars that you're seeing there, and then the costs slide in on the line plots there. And those lines are adjusted for inflation. And what's been slowly happening here is, first of all, we've been building more and more on the edge in the years, but also our infrastructure has been increasingly aging. And another thing that's been happening here is that our extreme events have become more and more frequent. Now, what I'm going to be talking about today is I'm going to start with a little bit of a 411 on climate change. And I'm also going to be then going into the impact of climate change on infrastructure. One thing you won't hear from me, I hate polar bears. We're not going to be talking about polar bears or any of that other kind of stuff. I'm talking about the impact it has on a lot of things that impact our bottom line, national security, et cetera. So let's talk here about a little bit of the basics of climate change. Well, this right here is really where the game plays out. It's the atmosphere, and it's also the energy budget of the atmosphere. So what you have is you have a certain amount of energy that's coming in from the sun, okay, comes in through the atmosphere. Some of it's absorbed by the atmosphere. That's what you're seeing there on the atmospheric and environmental science side. I guess for you guys, that's your right side. And the or left side, I have to do the L. And also it gets absorbed by the surface or it gets backscattered out to space. Now, when you also have this occurring, you have a certain amount of energy that's absorbed by the Earth and that energy that is also absorbed by the atmosphere. The atmosphere actually is a source of radiation. And if when you talk about things like the greenhouse effect in one of my classes and you say that the greenhouse effect traps radiation, I send you to the corner because the greenhouse effect is actually the atmosphere emitting radiation, both out to space and down below. And the rate at which the atmosphere emits is based on two things. It's based on the temperature of the atmosphere or the surface if you're dealing with a solid surface on the ground. And it's also dealt with the composition of the gases in the atmosphere, or again, the ground substances. And so what we've been doing over the several years as we've been increasing the amount of carbon dioxide, methane, and other gases that are very active in emitting in specific parts of the spectrum. And this is an example of this. This right here is a couple images. Pulled them up last night. This is from our GOES platforms. These are our operational satellite platforms. We use this same physics when we talk about climate change to do incredibly boring things like figuring out, for example, how the air is moving in the atmosphere, what the atmospheric profile is of temperature and humidity. And so what we have here on this first arrow that's popping up, what you're seeing here is one that's been used for years. This is the water vapor channel. And what you're seeing here is the atmosphere emitting because of the amount of water vapor that it has and also the level in the atmosphere at where the water vapor is. And what we use that for is we can use that to actually see flow in the atmosphere. If you look here, you can't see any ground. That's because you're looking at the atmosphere. The atmosphere is opaque in that part of the spectrum. And then the infrared part of the spectrum over here is another area, and this is an area that has just been added to the GOES platform's repertoire of imagery that it can pull. This is a band that is active in the CO2 absorbing band. That's one of the things that we are concerned about. It's used operationally in the Weather Service to look again at atmospheric flow, temperatures at different levels in the atmosphere. And again, it's really hard to see the ground in this because again, you are seeing the atmosphere emitting. And this winds up being a heat lamp. And this heat lamp is on 24/7, 365 days a year. It is always going in. And what we're doing here is we're also slowly increasing over the years due to industrialization and the burning of fossil fuels, for example. Also, there are elements of agriculture that contribute to it, areas of industry like concrete and cement production. But what's happening here is that over the years, we have been steadily adding to the carbon dioxide amount in the atmosphere. And though it's a very small amount of gas, it has an incredible influence on the radiation balance of the Earth. And what that has done over the years, this is courtesy of Berkeley Earth. It's a group that was originally hired to debunk global warming. And I say this is a former global warming lukewarmist, okay. They were brought in to, bring in questions about what the data was showing. And they were able to show, yes, it's us doing it. And yes, the temperature is rising. And so this is what you're seeing here. Again, a very steady increase in temperatures going up since industrialization. And another thing I often get is I'll have people ask if the climate is always changing. Well, let's look at the primary forcer. The primary forcer here is certain types of thermal infrared active gases that cause the atmosphere to be more efficient at offloading infrared radiation. And so what you have here is the total amount that we have been slowly putting into the atmosphere. The red is the methane on one axis, the other side is the carbon dioxide. Both of them are increased to much higher amounts than they've been in our history. That end of there, that's 8,000 years before present. So we're looking at effectively dawn of man. Dawn of man specifically, if I remember correctly, that's going to be where Neanderthals and Homo sapiens branched. Now, we also can go back to see how long it's been since we've had that much carbon dioxide in the atmosphere. And so what I have here is going to that little up vertical line on the far side under the years AD area. If I carry it back over here to the last time we were in this range, we're going back to as more recently as the Pliocene period. That is definitely pre-people. When we look at us, you're looking at Australopithecine and that type of thing. But it's been quite a while since we've had that much CO2 in the atmosphere. All right. And when we look at the impact it's had, one of the things we do to try to take care of is determine how much, for example, is being caused by solar cycles. And you're seeing that in sort of in the middle graph here. This is from the most recent IPCC Intergovernmental Panel on Climate Change assessment report. This is the 6th one. It just recently started coming out. And so what you're seeing here is the role, for example, of solar and volcanic drivers. It was an interesting weekend, not just for geologists, for meteorologists. We actually could see the pressure wave from the eruption go through our home weather stations, a lot of us, but the interannual variability as well. And what's happening here is that most of our drivers here are really being caused by humans. It's the kind of things that we put in the atmosphere. And that includes things like volcanic eruptions. The amount of volcanic eruption CO2 that comes in through volcanic eruptions is considerably less overall than what we put in. And the impact this has, impacts for starters, are global temperatures, and we're expecting it to continue to do so. So this is also from the AR6 report from the IPCC. What you're seeing here is the projected increases and current increases on the far side, where you can see an area of past, which is observed with respect to global temperatures, for example, and precipitation, and the impact that it also has on other attributes like estimates of sea ice area in the Arctic and also heat content in the ocean. Those have a shorter, reliable area of record. And so you have some areas that are simulated purely, others are backed up by observations, as you can see here. So the heat content in the ice, rather difficult to do without really good satellite analysis. And then when you do the air temperatures and land precipitation, really the best thing is there is rain gauges and thermometers. And we've had those for a while. So what we're seeing here is a rough expected increase in temperature as we move into the coming century. And we've also double checked, we've checked over and over again because nobody wants to be more wrong on this than climate scientists. We have checked to see if you just simply use natural forcing, if you have natural forcing and you just simply run the models without additional CO2 added by human activities, you get the tracks that you see on the right side of the graph. That's this one over here. I don't know if I can move my mouse. Apparently I can't. Can't do it at my classroom either. But in the gray plot over onto the side, you can actually see the green trace, which is representing just simply the natural and solar and volcanic influences historically. And then you can't get the observed temperature increases without adding the fossil fuel emissions, et cetera, land use change, aerosols that we have put into the atmosphere. Okay, and again, nobody wants to be more wrong than we do. Now, what this means for us, and these images are actually from the 4th National Climate Assessment. We pull these out every few years. We're actually right now working on NCA 5. In fact, when I'm coming off of this meeting, I have to join a teleconference on that to talk about the Northern Great Plains area, and that's going to be one of our workshops. But what's happening is obviously we're expecting a warming climate, and this is actually images from the NCA 4 reports. We are expecting for both low emission scenarios and high emission scenarios, as shown here, increases in our temperatures and also increases in our precipitation extremes. And that's what I'm showing here. These are precipitation events with more than 1 inch of rainfall. And what's happening here is these are slowly increasing over time in the coming century, as we expect. Okay, so we're going to be expecting a warming climate where minimum temperatures are really sort of expected to rise faster, just based on the math and the physics of the greenhouse event. As I said earlier, it's a heat lamp. It's on 24/7. So you're going to see the signal a lot more in some areas where the sun isn't burning down on you. So you're going to see that more in the Arctic, which we are seeing in observations. And in some areas, we're seeing increases in minimum temperatures. Now, you think that's great because you don't want to have cold temperatures, but we also calibrate a lot of our lifestyle, assuming, for example, that certain unpleasant things get frozen out. And as this continues, we could be seeing a rise in certain types of invasive species that don't get frozen out the way we've come to expect. And that's a concern that we have, say, with agriculture. The other thing we have is if we're going to be having higher temperatures, we still are going to be getting things like snow. All right, we still are going to have winter. However, the snowmelt frequency is going to be accelerated. So we are expecting an accelerated water cycle. And with rainfall, as you can see down here, and I've got some more plots to show that in a few, we are expecting to have, bigger pauses, say, between precipitation events, but they're going to make up for lost time in things like intensity. You can have the same amount of total rainfall in a future simulation, but you will have, in some cases, more extreme rainfall events and changes in that. And what that means is when you look at how we are designing our infrastructure, we're going to be in a situation where we're driving past our headlights. We're going to be having an infrastructure. In fact, right now we have an infrastructure that isn't always resilient to our existing climate. So that is another thing we have to keep our eyes on. So if we look, for example, and this is some stuff that we've done here at Mines, just simply examining how these are going to be affecting South Dakota. One of the things you almost always see here, it's one of the most consistent signals that we have with global warming is, yes, we are going to be seeing increases in our temperatures. And so on one side of the plot here, I have the Black Hills. On the other side of the plot, I've got the area East River. This is actually the climate zone for South Dakota that's centered over Brookings. So sorry, SDSU. Anyway, we meant to do that. Don't talk to us about weather modification, but let's get serious. What you're seeing here is the typical increase in both the maximum and minimum temperatures here. And with precipitation, it's a little bit difficult because, again, you can have a scenario where you do break even with rainfall, but also because of the temperature, you're going to have more evaporation. So you're going to have increased water deficits, but also the frequency of the rainfall we do expect to see modulated. And that's one of the things that we see. And that's one of the things that we represent when we're worried about infrastructure, because we're very often, for us, not interested in the average temperature. We're interested in the tails. We're interested in the extremes. So whether or not we have more extreme hot weather events and fewer cold extremes, or if we have events where we have fewer wet days and more heavy wet days, but they're going to be further and further apart. So that's a big concern that we do have when we look at this. And this is another example of some of the things that we've looked at here at Mines. This is one of our basins. I'm just breaking these down by watersheds when I did this project. And what you're seeing here is the historical scenario. And the historical scenario typically ends at 2005 for this particular set of climate simulations. At 2006, that's where it branches out into future scenarios with high, medium, low emissions, et cetera. And here what I have is I've bracketed what was then considered to be the expected upper and lower bounds, which would be what we call the RCP 8.5, meaning 8.5 watts per square meter more coming down at the end of the century than we've had. And the same thing with the 4.5 watts per square meter being shined down from the atmosphere. And if we just simply take a certain amount of rainfall, okay, say at 20 years, the 20-year return period from the simulations that we do are going to be on the order of, as you can see here, somewhere between 50 and 75 millimeters. In fact, it splits the difference perfectly. And that's why I picked it. And when you go over to our future scenario, and this is mid-20th century, this is a 30-year block where we're trying to get the average or expected precipitation ranges. If we use the low emission scenario, and yes, that line is flat, by the way. I've checked it over and over again. It's a bit of an illusion, the gray line. And when you see that line going down, basically that's saying that a 20-year return event could be a 14-year event, for example. And if we go to the high emission, we're looking at something that's even more frequent. So we are seeing an expectation where the frequency of our heavy rain events are going to be more and more frequent. And that's a big concern with the big events, but also if you go down to the lower events and start doing the same thing, the same approach where you go up, say, at a 6 return event and carry it over and see where it's going to intersect with the future traces, you're seeing that the shorter, more frequent events are actually going to be happening more frequently too, and that becomes another problem, and I'll get to that in a few seconds. But when we look at this also, it matters when we get our rainfall. And what you're seeing here is the precipitation anomalies over the Black Hills area. Specifically, I'm looking at, for the most part, the Cheyenne Basin in these images. And what you're seeing here, again, is mid-21st century versus the end of the historical period that we use. And what we're doing here is for a high emission and a low emission scenario, you're seeing the shifts in when we get that precipitation. And so what you're seeing here is maybe a little less total precipitation in certain months of the year, like summer, but again, expect them to be more intense. But notice what's happening, say, in the transition season that we have here. April is our winter here in South Dakota, or at least in West River, South Dakota. That's when we get our Colorado lows that slam snow up against the Black Hills. It's going to be wetter in the future as well. So yeah, this is going to be an interesting scenario that could be playing out, a shift in when we expect our rainfall. Now, another thing that we see, if we were to just simply look at this in different parts of the world, and this is not climate simulation, this is happening, as you can see by these dates. These dates are going from 1951 to 2015. What you're seeing here is really the different ranges in temperature over different areas of the world. And so what you're seeing here is, again, this idea of weather is what you get, but climate's what you expect. So these are the probabilities. And what you're seeing here is a slow gaslighting over the years that we've been having, with some areas becoming increasingly warmer and warmer. Now, another thing that sort of keeps me up at night is that we have a major expectation with both our climate systems and our designed environments, which is called stationarity. It's basically status quo. We expect certain things to not change over long periods of time. That's why we design for a certain type of flood, and it's based on historical climate data. That's how we still do it. And another thing that does tend to rise a little bit of anxiety is, let's go to some other parts of the world. These are parts of the world that also keep other people awake at night for other reasons. And as you can see, these changes are also happening in these areas. They're happening, in fact, in some cases, much more than areas where we live. For example, I don't have Ukraine, but I do understand that there is some battle space meteorology issues about being able to move tanks around on the ground in that area. That's something I did in a past life, where once again, the idea is that if you have early thaw, well, that's going to be harder to move tanks around and things like that. So NATO actually does have a concern about this type of thing. So does the US Army in general. They have an entire organization that's out to look at how cold climates are important to our battle space. But another thing that I do want to kind of close out the Climate 101 section on here is to answer a question that we very often get. And that is when we have an extreme event, we have a hurricane, we have forest fires, we have, for example, the thunderstorms and tornado outbreaks that we had a ways back. Is that particular event driven by climate change? Well, this is a very difficult question. And when we look at this, the National Academy of Sciences actually did a study on that. This is what this figure is from here. They did a study on attributing weather events to climate change, and it talked about the state of the art. And one of the things that you have is you really have sort of a two-metric test, because in some cases, if you look at the axis going in the horizontal direction, we have an understanding of how the physics of climate change, what we expect to happen, is going to alter the overall general environment. So for example, we know that when we have a larger, warmer climate, more warmer temperatures, what we're going to be getting is we're going to be getting more heat waves. Okay, there's going to be also changes to our extreme cold patterns. We are going to have a good feel for extreme rainfall because we're going to have more potential for convection. We have more potential for droughts. So you're seeing those at the higher end of the axis there. And then we have questions about things like severe storms. Okay, we have a big question as to whether or not one of the key factors in predicting severe storms, which is wind shear, wind changing with height, is going to change in the future. So we do have a little bit of uncertainty there. We also do know, for example, that wildfires, hey, you have warm temperatures, you have warm moisture deficits, it means more fuel on the ground. But when it comes to determining individual events, it actually can be rather difficult in some cases because you have to do what we call an attribution study at that end as to whether or not that particular event would be more likely or just about as likely as it is to happen with climate change and without. And there have been studies on specific events. A good example is the hurricane that hit Houston several years ago was found to have not been able to produce as much rain as it did if you didn't account for global warming impacting Gulf sea surface temperatures. And so that was a big study that came out from NCAR a few years back. But that really is what you're seeing here is really an environment where we have potential for more extreme events. It is a little harder to determine whether or not any individual extreme event is tied to it. You have to do a lot of counterfactual studies with simulations with global warming and without global warming being added to the models. And also you can do probabilistic studies as to what we've expected over the last X number of years as to what's the probability of event compared to what it is now. So that's kind of where we stand there. Now that is basically the idea of the basic climate change. That is the threat, if you will, on top of the infrastructure problem that we have. And so we have an environment that's increasingly playing more and more rough with our built environment. And we have a number of factors that are not working in our favor. For starters, a lot of our infrastructure is aging. Okay. If you look at, for example, a lot of the dams in South Dakota, the smaller wreck dams, for example, a lot of them have been built a long time ago. All right. Some of them actually date back to the WP era, like 60 years or so back, even further. And the other thing is that many of our design codes do not necessarily account for a changing climate. They lag because we have to go back in time and determine what the normals are very often. We don't really use a lot of future projections in this area. This is something that ASCE is very concerned about and has a couple committees looking at the more upcoming building standards in that area. Another thing, for example, is a lot of our really good stuff is even stale. One of the atlases, the data sets that we use to determine storm return periods, it was basically revised in the basically before 2010. And some areas are still using much older results like in the Pacific Northwest. They have not been able to update those records yet. It just takes time to work through those. And so some of those are working on storm returns that were calculated during the 70s and 90s. So that is again, we are dealing with a lot of stale information for our planning. And as I said before, our infrastructure isn't really resilient to our existing climate. If you look at, for example, the ARPA surveys, these come out every few years. It's the American Road and Transportation Builders Association. And what they did for South Dakota is they go through, and they do it for other states, they determine which states, which bridges are deficient, et cetera, which ones need upbringing and updating. And really 17% of our bridges were structurally deficient. And if you actually go to the ARPA webpage, you can actually see the bridges that they really are concerned about. And there are a couple in Sioux Falls, there are a couple in Rapid that have raised some concerns. And again, all of this is happening while our climate is slowly being modified year after year after year. And so what the ASCE has done is they put out this product every few years. It's called the ASCE America's Infrastructure Report Card. And this is the one from 2017. They gave us, the country, all a D, or a D plus, I should say. We don't even, when we had plus or minus grades at mine, some of you may remember, we didn't even have a D plus, we just had D. Now, this is the more recent one. This is for 2021. And they upped it a little bit. It's a C minus, okay, not great, not terrible. But the rubrics that they use are, for example, looking at capacity, the condition, what funding is going in, and then they go into things like future need, resilience, et cetera. And these are the areas where the committee I'm on with ASCE has been working in order to determine what our needs are required in order for us to update, for example, what our infrastructure would look like if we use the weather in 2050, for example, to force our current systems. And there's a broad range of things that you see here as far as what they're looking into. And we prioritize them. You try to figure out which are the ones that are the most vulnerable. And some states actually do their own. And sometimes it works really well. And then you have this case. This is Texas. This is their energy report card grade that came out in February of 2021. That was about concurrent with the big freeze. And they gave themselves a B+. So they don't always do it well. Usually it's separate from the national assessments. South Dakota, by the way, doesn't have one. We do not do an infrastructure report card. It takes a lot of work to do that, okay, to go through there and do the full assessment. Yeah. But overall, there's a lot of things that we have to look at. For example, we look at things like the temperature impacts and precipitation impacts, say, on agriculture sector. We are an agricultural heavy state. And so, for example, if you look at, say, our current analysis, now that says 8.5, but there's not a lot of change at this early stage of the game based on the existing climate. So you're seeing sort of, it's not that different from what you see over here on this side. But that's, again, that's 2010, 2019. So that's more concurrent. Now, if you move forward to 2050, you see a couple things here. You see a definite change in the temperature drifting further and further north. You notice, however, that you don't see a major change in projected total precipitation. Again, this is not taking into account seasonal distributions or extreme events, but this would impact what can be planted, what can be grown. And if you've ever seen one of these are the zones of plants, so I can choose which plants die in our yard. This is the classic USDA plant hardiness map when you try to figure out what flowers you want to plant. If we were to apply that, again, the same metrics that they use, what we also have are, and these are usually based on minimum temperatures. So what you're seeing there is a change, slow up north motion of our freezing temperatures or our cold temperatures. And what those are representing is, again, things that we expect to see frozen out are not going to be as frozen out as time proceeds. And that does include things like bugs. Right. Now, when we look at rainfall, one of the other things we are expecting, as I said before, are changes in the extremes in 24-hour rainfall, for example. This is one of the classic metrics because 24-hour rainfall is one of the easiest and most frequently measured rainfall totals that we have. We do have some regions and some stations that measure it at a much more frequent state, but what you're seeing here again is a slow increase in precipitation extreme events there in that area. And for us, you can see this map. This map is totally brought up at random. I hope people recognize where that is. That is actually the Mines campus. Some people don't realize how close Rapid Creek is to the campus. Okay, but what you're seeing here is the current delineated flood maps. And this is based, again, on past climate. This is something that needs to be updated across the country in order to be weather ready for future weather extremes. And so you see here the 500-year and the 100-year flood. You may have heard about the flood that was, I believe it was somewhere, it was in the Northeast. It's one of the dams, and I cannot remember, so like Hidden Valley Dam or one of the hidden dams that's up there. That was a dam that broke a couple years ago, and the bucket survey reported 10 inches of rainfall over those areas. The observed through our official networks was about as high as 6, but even those are extraordinarily high return events. And the question is, how often are we going to be getting that kind of a flood, both with respect to the weather that's coming down and the ways in which we've altered our ground environments on the ground as well. So that's going to be a big issue that we're going to have. And another thing for people in the agricultural sector, this is an older study, but you can actually see one of the other reasons that we're concerned about increased rainfall frequency. For example, what you see here is the sediment discharge in the Bad River. Now, this only goes up to 1996, but you can see what basically happens with respect to the discharge of sediments into a river system. They typically, most discharge happens only with a very small number of precipitation events. That's the black in the stack bar chart here. The ones that happen over 90% of the year, that's the yellow. It doesn't do a whole lot. So one gully washer, one toad strangler is going to be responsible for a lot of the sediment discharge into our river and lake systems, and those get pushed downstream. Another thing, this is another couple images taken at random. I'm from Eastern North Carolina, and the first one is actually from the Outer Banks after a major storm event. So that's a singular event right there. And I'm curious, this is usually where I do this with my students. I ask, where do you think that lower picture is from? Well, it's another Highway 12. It's US Highway 12. US Highway 12, this is actually an area in eastern South Dakota, northeast South Dakota. And what's happened in northeast South Dakota is really extraordinary. What happened in 1984, if you look here, you have a Landsat image. These are 3 generations of Landsat seeds. And what you're seeing there is the lake levels down at the bottom. Now, the person who takes those lake levels at Wabae Reserve, she retired. So we don't have some of the more recent ones, and I'm a little bummed about that. But what you do see here in the Landsat scenes is a marked increase over time in the amount of water on the surface. And these are, if you're familiar with the northeast corner of the state, it's called the Prairie Pothole region. What you have here are very shallow depressions. So it's not how deep the water is as much as it is how wide. A small amount of volume creates a huge change in surface area. And that's what you're seeing here with the status quo for most of our time in this region was represented in 1984's image. But as things started happening in the 90s, there was a huge uptake in water coming in. It happened about right after the Red River of the North flooding. And it never went down. What we now have is a controlled system where we have in 2011 this rather high amount of water. And if you look here, I literally just pulled this off yesterday. This is from summer of 2021. These are all from the Landsat platforms at the time. And you can see we're basically still in that same regime in 2011. But that's one of my more shocking images that I tend to look at when I look at changes in climate. The other one is looking at changes in sea ice in the Arctic. I don't have those because I'm trying to stick with South Dakota, but that was one of my first jobs as a real meteorologist, was to map snowmelt on the ice in the Arctic. And when these better imagery started coming out, we'd look at it and just see how things have changed. And really, I can't see the same forms in the ice opening up and melt patterns that I saw when I was a young college student with my first real job. And that's really alarming for me from a strategic perspective, because that's going to be a very new area of headbutting between a number of powers in the Arctic. All right. But when we also look at this, there's another problem that comes up, and this is a more mundane issue. It's one that people tend to forget about. When you saw those 2 images earlier with both Highway 12s, you had one event that was an extreme event. That event was one big, single, infrequent event that had a high cost on regional structure. Now, let's consider something else that's happening. As you saw in the earlier plots, not only do you have more frequent extreme events, but the smaller, less frequent events are also going to become more frequent. We call those nuisance events. Nuisance events, as I like to say, are passive aggressively just below your insurance deductible. So when you have the big cost, that's going to be where large amounts of relief effort comes in. Okay, more capital starts coming into an area. With the nuisance events, very often it is shouldered by the property owner or a municipality. So when you do this, this is a study that was by one of our colleagues on the ASCE committees. They basically tallied up the amount of cost overall of these events with respect to the extreme events and nuisance events. They were focusing on flooding. And what happened was they found out that those were on par with each other. Okay, so, and think about that. They're on par, but the burden of the costs can be extraordinarily on par with one another. And again, the shouldering of the cost winds up being, in one case, more on the consumer than it is on the larger population. Now, here's another example of nuisance events. This is king tide flooding. King tide flooding. This is I think Fort Lauderdale in Florida. And this is a problem that's happening up the southeast seaboard, where you do have high tides coming in with what we call clear sky flooding. And so you have periods where, in some of these cases, these coastal communities are paying more and more to de-flood or pump out water from some of their lower lying infrastructure. And so that is a big concern. And that's a cost that, again, that's an example of costs that are being shared by municipalities. Okay. You also have some areas, for example, on some of the bases around Norfolk, where it is becoming harder and harder on certain days for people to actually get on base. And that's something that the Navy is very concerned with. Now, another thing when we look at this is a simple reality. We do not necessarily build all of our environments, okay? We don't build all of our environments to withstand all of the events that we can get. There's only so much that we can do and remain cost effective. And so, for example, again, if I take two random cities, okay, one's Rapid City, the other one is my hometown, and you just take a hypothetical probability of an event. This is just a generic pair of traces here. Both of those two communities would have a very different expectation if they wanted to be able to survive a certain percentage of extreme events. Okay, if you take the area under the curve, and that's what you do when you do probabilities, it's never the actual graph value, it's the area under the curve, as I tell my students. It's all about the integral. You would have a very different design expectation for something in Rapid City than, say, in Eastern North Carolina. And that brings up the other issue. Things break. So what do we do when things break? This is something that's called the cycle of resilience. This is just one example of one of those charts. And typically what you have is you have this little cycle. What you start off with, all right, is you start with an area of civil preparedness. So you have the outreach and you know what to do, for example, when you have a flood. There are areas, say, in the Front Range of Colorado where they have signs that says when you have a flood, get out of your car and run uphill. All right. Others, other types of things, don't drive into flowing water, because a very small amount of water can push your car downhill. And you know what's downhill? More water, deeper water. So you'll hear us do that as meteorologists, turn around, don't drown, for example. You have things like don't build on a floodplain. But what defines a floodplain? Okay, there you go. But at some point, what you get is you get an event. You get an event that breaks the stuff that you built that you hope was going to be resilient for most events. Well, for starters, okay, the first area after that is going to be the response. That's the holy crow. We now have to go and take care of the people. We have to do damage control, et cetera. And then there's a point where you catch your breath, and then it's time for everybody to start recovering. People are, once again, putting things back together and rebuilding. And then you get to the next phase, which is prevention, and then you're back in the preparation zone. Our attention is going to have to increasingly be on that recovery and prevention area, in which we do want to start thinking differently. And you want to see an example of some of this? Okay, this is another one that I throw at my students until I realized, and one of the students pointed out with my bad eyesight, that the name was on the sign. This is actually from the Black Hills flood. This is the road leading into Chapel Lane. If you want to go visit the staff kirk, you couldn't do it at that point for a very simple reason. There was no other way to get in. All right. And so this is actually one of the bridges that is listed as impacted from the bridge survey, by the way. But what you see here is the Rapid Creek flood. And one of the responses that we had to the Rapid Creek flood was, well, there's still only one way to get out of Chapel Valley, but we also have an extended floodplain that is where a lot of the properties that were destroyed were. Okay, so that's one example of one way of strategizing it, the idea of green spaces. But one of the things we're going to have to start doing more and more is to start looking at future climates. Okay, we're going to have to start looking at possible changes in storm frequency, for example, wind loads, snow loads even. And this has been discussed with a couple different options. This includes things like flexibility between, I'm checking time, sorry. All right, flexibility between natural structures like floodplains or marshland and built designs, making things that are big projects. And in some cases, they're actually clever projects. So I'm going to tout one of my colleagues from the ASCE committees on that last one. Yes, that does say Emerald 2.2. And but what you see here is an example of a megastructure. Okay, that is the idea of a Thames barrier. You also just have the idea of shoring up your bridges against floods. Again, increasing the natural environment along your floodplain. And in this case, what you're seeing here are little mats that float on, in this case, she was planning for these to go out into Boston Harbor. And they are little round, little platforms that float. And they have green vegetation on them. So they look pretty and they're nice and pleasant. And you can actually space them depending on how much wave action you want to break. That's actually a really cool feature of them. But again, they're called green tutus, and they're planning on seeing if they can deploy them in Boston. It also expands your park space, if you will. You can have nice little walkways in the middle of it. They're kind of a pleasant environment. Win-win for everyone. The other one is on the other side, okay? And that is building for future failures. And in this case, we often have this idea now being discussed called graceful failure in design. So for example, we have a senior design project over in civil where they were talking about working on, and since you are alums, you know the lay of the land here, so I don't have to go into too much description. But if you go across over toward the fairgrounds, you need to be able to cross Rapid Creek. Well, if you want to cross Rapid Creek, well, Rapid Creek is prone to have high water events. Okay, we had, of course, the notorious one in the early 70s. But the idea there is, okay, if you have a footbridge and you have way too much stream flow that can put that footbridge in jeopardy, instead of having the footbridge wash out, how about have it so that it breaks off at one end and swings open, and that way you just put it back in position. That idea is something called graceful failure. Graceful failure is the idea that, yeah, your stuff's going to break, but what you want to be able to do is make the recovery a lot easier and a lot faster. If you've ever seen me as a prof and you go into my office, you'll know that we have a Lego problem in our family. This is a good example. I hope I didn't spoil the first season of Mandalorian for you there, but it's a simple statement that we say whenever something falls, yeah, Legos don't break, they just disassemble. So the idea there is not having something that completely is destroyed and needs to be built from the ground up, but it increases the time of recovery. So those are the kind of options that are available in infrastructure that we think should be implemented in the future from some of the committees I've worked with. Now, that's really it. I probably have gone on a little too long, but I'm here to field a couple questions.
I think you're okay. If anyone does have questions, please put them in the chat box or the Q&A, and I will read them out loud. So I do have one from Ken Miller. It says, why the reliance on the RCP 8.5 scenario? It was categorized as the 1980-ish business as usual case with a no policy for GHG emissions, i.e. coal continues to provide 50% of world electricity.
There are two scenarios that you'll typically see used with the previous climate assessment. And when we work with the 8.5, the 8.5 is typically the high end, and it's almost always coupled with a low end scenario. So for example, you'll have those operating as sort of end members. And that's really the way in which you're supposed to be using 8.5 in decision-making environments. There are people who do say that that's the only one that they use. That is not necessarily what you should be doing, and you should be calling it business as usual. That's another thing where I will stand you in a corner. Some people do use that phrase, and I don't approve of it. We also, again, use a spectrum of events and ranges. Unfortunately, there are two issues when we start presenting results. You can only present so many. That's why we use the high end and the low end, the 4.5 and the 8.5 together very often. There's a new set of scenarios where they've lowered the pathway emissions at the end of the century for their end members. I think they're now going down to, I think 7. I'd have to go back and read the reports. These are all just coming out now. But yeah, you usually use the 8.5 in the context of another simulation. When you look at the literature, the 8.5 is more frequently used with the 4.5 or another scenario than it is standing out by itself.
Thank you.
Mhm.
Okay, I'll look. Yeah, if anyone has any questions, please feel free to drop them in. Oh, okay. Ryan says, we saw a lot about the temp and rainfall change over time. Do any of the models show if the wind strength or frequency will be changing?
I'm really interested in the wind, but when we work with the downscaling of wind speed, the downscaling of the wind speed is usually not one of the products that get produced. It has to do with the volume of data, and I would be very interested in that. I am very curious in seeing, for example, whether or not we expect winds to increase or decrease. That is one of my curious areas. I think we have to do a lot of downscaling of the larger scale simulations. And what I mean by downscaling, I mean, you take, for example, the global climate simulations, and then what you do is you use them to drive smaller models, more detailed models, and use the physics of the detailed models to figure out where the wind is. But I'm interested in both the changes in wind. Another thing that I'm interested in is really the role of the, for example, where the Colorado lows form, and are the Colorado low storm tracks changing? We're going to have a student working on that, actually. We're just getting him to do that.
Okay.
Question about Pacific.
2 questions. One came in from Jerry. It says, I'm in the Pacific Northwest. Do you know if atmospheric river events are significantly increasing in frequency?
I'm not sure that they are increasing in frequency or that we're just noticing them more. I do think that there is definitely a much strong, as the tropics begin getting warmer and warmer, you are going to get more and more water in play. So again, if you're looking at the attribution for climate change, you have 2 factors. You have the issue of working with what climate can modulate and what it actually is modulating. And there definitely is a capacity for more water in play, which means you have more atmospheric rivers that would be coming in. So I would say that part of the attribution cycle is part, I would be able to attribute that to climate change. The actual events, I'm not entirely sure yet.
Okay, and then another one asked, what is the most urgent to consider for residential? It must be, what's the most urgent event to consider for residential construction? I might have read that wrong, but
is that the one that's the for residential construction?
Yes.
Residential construction, I would probably say, well, in this area, hail. I think it's anecdotal, but we've noticed more hail over the last several months. But I would say in residential construction, there's another issue that we've had over the last couple of years, and that's freeze thaw. February of a few years ago was a very good example of that. But I would definitely look at making, if you're talking about just residential construction, I would be more worried about just simply the insulation on your household, making it more, for example, more insulated, so you don't have to burn your AC as much because you are going to be burning your AC more. I also would consider roof strengthening with respect to hail frequency.
Would that count for
I'm thinking about a couple other things too. Street repair and freeze thaw. And that's one that kind of hits me a little harder because freeze thaw hit our house and driveway very hard during the last deep freeze we had in February a couple of years back, where we had the freeze and then it would be just above freezing at the surface. It would still be bloody cold and it would just basically tore up our driveway and our steps.
Okay. Would that count too for what happened in like Texas? Like people, like what happened this past, almost a year ago in Texas and the southern states? That would be a residential effect on how to prepare your house, I guess.
Well, that's also, well, that's a lot of it. It's infrastructure as well, because the big problem in Texas was you have a situation where their supply lines for natural gas and things like that, they're under the ground. They're hardened under the ground. The areas on top, the distribution points, they had a problem in that area. Some of those areas were freezing above ground. And that's more of an ERCOT issue. That's where you basically need to have a situation where you're hardening your events against the freezing up at the front. And we've known about that since the last freeze they had. We were warning people to harden their stuff.
So we did have a question that came in. This is, what can we as alumni do to advocate for more climate resilient infrastructure as the state and nation?
If you're an engineer, there is right now the current standards are being reassessed. And if you're a member of ASCE and you can get involved in those processes, I would definitely recommend that. Also, just simply as members of a community, I would recommend, talking to your government. And again, I'm not able to lobby or anything like that in this capacity where I am today. But simply put, if communities are creating resiliency plans, make sure that it does include things like climate change and be resilient and ready for, open to the extremes that can be in the future. Mm-hmm.
Okay. And then we had another one came in that said, getting back to climate change 101, we are typically presented with downside effects or doom and gloom scenarios. Are there upside or positive aspects? And he said he did appreciate the in-depth scientific analysis you presented.
There are going to be areas that are going to have fewer freezes, and that does impact things like agriculture. Now, for example, there are projections, for example, that Canada is going to have certain better, more agricultural opportunities. One issue with Canada, though, is that it is also controlled by the amount of sun that comes in for plants and also the soils. But there are going to be some areas that could benefit from it. But overall, if you look at the global situation, we are looking at, again, the increases in extreme events, I think, is one big issue. And again, some of these are below disaster level radar. They become what we call nuisance events. There's also, for me, the national security side of things is one of the things that has me a little bit alarmed. For example, the battle space in the Arctic and also weak states down below. Some areas are going to be less cold, all right, but that less cold is going to be coupled with some other features that are not as desirable. Okay, even the areas that are less cold, you start having to worry about those. Mm-hmm. Mm-hmm.
One of the attendees asked could you share your slides with me, and then I can get the slides to them when we're done. Yeah. Okay, Stuart, if you send me an email, I'll put my email in the chat. Mm-hmm. So if anyone would like the slides,
I'll have to PDF them because it's in Keynote. If he has a Mac.
Yeah. So yes, I will get you the slides, but I will put that in there. If you email me and just remind me. So we had someone who had to leave, but he did have a question. However, your change in planting zone for susceptible plants to freezing seems to be based on average temperature. Yet isn't plant zone based on likelihood of low temperature killing of plants?
It's low temperature. So that was the low temperature based, yes. Mm-hmm. So I used the same algorithm. Mm-hmm.
Okay. And then we had Doug says, what is the outlook for hydroelectric power production in light of changing precipitation in the West, i.e. the Colorado River Basin, or e.g. the Colorado River Basin?
That may be one of the things we're talking about in about an hour. I'm actually not sure about that part of it. One thing is that if you do have hydropower that is mostly provided by snowmelt or a slow thaw in the snowmelt, that's going to impact some elements of it. One problem also when we start talking about increased temperatures is that does change the lake temperatures in the reservoirs. And there are people who are a little concerned about things like algae blooms and things like that, more of the biological response. I am not sure about how, for example, specific hydropower interests in the upper Missouri response is. I do know some people who are doing that. I probably could go back and look. Okay. Wish I had that one on my fingertips.
There are a lot of questions coming in today.
Mhm.
Oh, one more. Carl says, out of the climate change based on computer models, how many have proven out?
When you look at the temperature rise, if you take the ensembles, and this is how we do it, we actually run models for the past, okay? And that's how we spin things up to work into the future. But we run multiple models. And so, different countries, different institutions have their own models. And what we do is we put them all together and we call that an ensemble. In operational meteorology, we do that as well. We actually will run a model over and over again and get a spread of possible conditions. And when you put the spread of all those models together, the temperature trace of average global temperature actually tracks it rather well. You have to basically make sure that you're comparing apples and apples. So if you're doing surface temperatures, you do need to use the surface temperatures from the model. But yeah, I mean, they tend to track very well in that area. The precipitation as well, overall, with the ensembles of the models, they do fairly well together. The thing about models is that every model does something really well. And if it doesn't do well, there's another model that can usually cover it. That's one of the strategies behind working with ensembles.
Love that. It's very interesting to hear.
Also, things with the expectations of things happening in the Arctic, these have been in the models as well, and they've been tracking those.
Okay, well, we've reached the top of the hour, and to be cognizant of Dr. Capehart's time, because I know he has other meetings today.
I kind of need an excuse to avoid it, though.
I'm sure this is an interesting topic. I mean, there's a lot to talk about. So do you want to put your email in the chat and send it to everyone if they have questions?
I thought I had it in the slide.
Oh, you probably did.
I do. How do I put it in the chat?
Yeah, just to be safe. And if anyone has any questions or anything they think of afterwards, and I'll watch for it to make sure it goes through. It's at the next to share screen. But I might, if you can't get it, I can throw it in there too for you.
What I do teaching by distance, I can't see because I'm old and my body's broken. I can't see the little tiny things at the bottom, like the little numbers that pop up.
So, oh, there he goes. You got it. Oh, wait, hold on. We got to switch it to everyone. Hold on.
Oops.
That's okay. It happens. Okay. I got it to everyone. If you have any questions, please let Dr. Capehart know. As always, we always look for survey feedback. So if you have any thoughts, feelings about the webinar, please put it in I dropped the survey link, and then just to thank you everyone. And just to talk about kind of what's going on. We have this month is almost over with. So Monday, January 24th, admissions is going to give a presentation at 5 p.m. over Zoom, talking about navigating the college search at South Dakota Mines. And then I'll drop all the registrations in the link. And then February 3rd, we are having a department update from the camp department. I know there's a new name, and I know it's not Center for Advanced Manufacturing Production. I know they have a different name, but the camp department is going to give us a update. And then February 17th, we're going to have another Lunch and Learn will be about the avionics program here at campus, which is new. So I dropped the links in the chat if you'd like to register for those. I will send out email reminders. I appreciate everyone coming. Again, if you have any questions, please let us know. And then, oh, there we go. Center for Advanced Multidisciplinary Projects. That's what it is. Thank you, Dr. Rankin.
Another penny for the acronym jar.
Yes, so I get for being on campus for a really long time. I'm stuck in the old ways, but yes, I really appreciate it.